I want you to just take a second and picture the floorboards of a high-performance electric vehicle.
Right.
Like you're driving down the highway, it's a perfectly smooth ride, the cabin is, whisper quiet.
Yeah, totally serene.
Exactly. Maybe the AC is just lightly humming in the background. But right underneath your feet, encapsulated in this thick metal housing, there is a violent, invisible war happening.
A literal war of thermodynamics and electromagnetism, honestly.
Yeah.
And it's playing out at a microscopic atomic level.
It's wild. And today, we aren't talking about the typical EV talking points, right? We aren't looking at battery chemistry or range anxiety or the aerodynamics of the chassis.
Right.
We are talking about the ultimate enemy of high-performance electronics.
Which is extreme instantaneous heat.
Yes. Welcome to the deep dive. Our mission today is to unpack a highly specific, high-stakes technical protocol straight from the engineering front lines. So we are looking into the inverter and power stage over-temperature diagnostics for IGBT and silicon carbide MOSFETs in dual motor controllers.
I love how incredibly specific that sounds.
It's a mouthful.
It really is. But, while it might seem like this niche engineering document, the implications of this protocol touch every single person who gets into a modern electric vehicle.
Right.
We are talking about the absolute limits of material science here.
And we're talking about ASIL D safety standards.
Yes, the highest of the high.
Yeah, for those who, track automotive engineering, ASIL stands for Automotive Safety Integrity Level, and the D dictates the highest possible classification of safety critical functions.
It's not just a suggestion.
No. It's reserved for systems where a failure doesn't just mean, like, a check engine light coming on. It means a high probability of severe, life-threatening injury.
Exactly.
If the systems we're unpacking today fail, we aren't just looking at a bumpy ride. We are talking about a catastrophic core meltdown of the motor controller, and that triggers unintended, uncontrollable torque.
Which is terrifying when you map that to the physical world.
Oh, absolutely.
I mean, a failure here could mean your car suddenly accelerating at maximum power on its own.
Wow.
Or violently locking up the wheels while you're doing, 70 miles an hour on the interstate.
It's literally life or death. So we are going to explore this entire invisible war today. From the brutal physics of a silicon meltdown, through the predictive software trying to stop it, all the way down to the almost sadistic factory torture tests designed to ensure these components never fail in the real world.
They really do torture them.
Oh, they do. But before we figure out how to stop a catastrophic failure, we have to understand the physical chain reaction that causes it, right? We need to look at the anatomy of a meltdown.
Right, the fault root cause analysis.
Yeah.
Because to engineer a bulletproof safety system, you first have to deeply, intimately understand the destruction you're trying to prevent.
So let's set the scene for the listener. You have a high-performance EV, you step on the accelerator. The dual motor controller, the power control system, or PCS, is the middleman. Its job is to take the direct current, the DC, coming from the massive battery pack, and chop it up.
Yeah, literally chopping it.
Translating it into alternating current, or AC, that actually spins the magnetic fields inside the motors.
And the muscle doing that chopping is this microscopic piece of silicon, or increasingly silicon carbide, the power chips.
Right.
The documentation specifically refers to IGBTs and SiC MOSFETs.
Let's define those right out of the gate, actually, because that material difference sets up the entire thermal problem.
It really does.
So IGBT stands for insulated gate bipolar transistor. We've used them for decades. They're silicon-based, highly robust, and great at handling high currents.
But the industry is rapidly shifting toward silicon carbide MOSFETs.
Yeah.
Silicon carbide is what we call a wide bandgap material.
Wide bandgap.
Yeah. In atomic terms, the electrons in a SiC crystal require a lot more energy to jump the gap into the conduction band compared to pure silicon.
Which, I mean, that sounds like a bad thing initially, right? Like, why would you want it to be harder for electrons to flow?
Well, because that wide bandgap means the material can withstand vastly higher voltages before breaking down.
Oh, okay.
And it can operate at significantly higher temperatures. But the real magic of silicon carbide is how fast it can switch.
Right.
It can turn on and off at frequencies that make traditional silicon look like it's moving in slow motion.
But that speed comes with a massive penalty. Every single time those transistors switch, and we're talking tens of thousands of times a second, there is an astronomical spike in electrical stress.
Huge stress.
The documents refer to high dNdVdt.
Yes.
Let's break that down for the listener, just so we're all on the same page.
So ddt is the mathematical derivative of current with respect to time,
Mm-hmm.
basically the rate of change of current.
Okay.
And DDT is the rate of change of voltage. We aren't just talking about a lot of electricity moving around. We're talking about how violently fast the electrical state is shifting.
Right.
Imagine taking 800 volts and hundreds of amps and forcing it to zero, then back to maximum in a fraction of a microsecond.
And because of the inductance in the wires and the motor coils, that sudden change in current creates an inductive kickback.
Right. It fights the change.
The electricity doesn't want to stop moving.
Exactly the problem. And this high-frequency switching is not perfectly efficient. We have two major types of loss generating heat inside this tiny chip.
Okay, what's the first one?
The first is switching loss. A transistor isn't magic, It physically takes a tiny fraction of time to transition from fully closed, where it's blocking voltage, to fully open, where it's conducting current.
Right.
During that microscopic transition state, the chip is simultaneously experiencing high voltage and high current.
Wait, if the chip is switching 10,000 times a second, that inefficient transition state is happening 20,000 times a second.
Exactly.
Because it's on then off. It's constantly caught in that high friction middle ground.
It adds up incredibly fast.
Yeah.
And that's just the switching loss. The second factor is conduction loss. Even when the transistor is fully perfectly open, the silicon carbide still has physical electrical resistance. When you push massive amounts of current through it, you get a voltage drop.
Right.
The formula is beautifully simple, but brutal in reality. Power loss equals current squared times resistance, I squared R.
Current squared. Meaning if you double the current to accelerate harder, you don't just double the heat, you quadruple it.
You quadruple the heat.
Man.
So you have massive amounts of thermal energy accumulating exponentially inside a microscopic die that is like no larger than a postage stamp.
Wow.
If that heat cannot escape the chip faster than it is being generated, the junction temperature, which is the literal temperature inside the atomic lattice of the chip, skyrockets into a thermal runaway.
The analogy I keep coming back to is a massive heavy-duty industrial light switch.
Okay, I like that.
Imagine violently flicking that switch on and off 20,000 times a second. The sheer physical friction of doing the electrical friction causes heat to build up instantly. The silicon is just absorbing microscopic blows over and over and over.
And that heat needs somewhere to go, right?
Right.
The architectural heat path is designed to travel down from the silicon die through a ceramic substrate board, out to a copper base plate, and finally into a liquid cooling system.
Okay.
But to transfer heat efficiently between two solid, rigid pieces of metal like the module and the heatsink engineers use a thermal interface material, a TIM.
Just like building a gaming PC.
Exactly.
You put that little dab of silver thermal paste on the CPU before you bolt the fan down. You do that because microscopic imperfections in the metal surfaces would leave air gaps, and air is a terrible conductor of heat.
Air is practically an insulator in this context.
Right.
So the TIM fills those microscopic valleys. But in a consumer PC, that paste sits in a nice climate-controlled room.
Yeah.
Under the floorboards of an electric vehicle, this paste is subjected to a completely brutal, violently changing environment. And this introduces the second major root cause of failure the engineers are fighting, the pump-out effect.
Because an EV operates in freezing winters, right? Down to minus 40 degrees Celsius in places like Norway or Canada.
Sure.
But then when you floor the accelerator, the silicon chip itself can heat up to positive 150 degrees Celsius under load. We are talking about 190 degrees Celsius thermal swing in a matter of minutes.
And we have to look at how different materials react to that swing. This is the coefficient of thermal expansion, or CTE.
Okay.
Everything expands when it gets hot and shrinks when it gets cold, but a silicon die expands at a totally different rate than a copper base plate.
Right.
And that expands at a different rate than the aluminum housing.
So it's like a microscopic tug of war?
A violent one.
Yeah.
This constant expanding and shrinking at varying rates across different layers creates intense thermal mechanical stress. It causes the metal plates to literally warp, bowing inward and outward.
Which means it is constantly squeezing and releasing the thermal paste trapped between them.
Exactly.
It's like taking a full tube of toothpaste, leaving the cap off, and repeatedly freezing it solid, boiling it, and stepping on it.
That is precisely what happens. The cyclic warping physically forces the thermal interface material out from between the layers.
Oh, wow.
The paste gets pumped out, or the extreme heat just bakes the oils out of it, leading to what we call dry-out aging.
And when that paste migrates out, it leaves behind those microscopic air gaps we just talked about.
And here is where the physics turn deadly for the module. Suddenly, the thermal resistance at that specific interface spikes exponentially.
Because of the air.
Right. The heat traveling down from the chip hits that microscopic pocket of trapped air and just stops.
Yeah.
It cannot cross the gap efficiently. So it bounces back, it pools.
The emergency exit for the heat is suddenly bricked over.
Yeah.
The chip is still flicking on and off, still generating I²R conduction loss, but now the heat is trapped. But the degradation isn't just happening at the paste layer, right?
Yeah.
The actual metallic connections inside the chips start tearing themselves apart.
Yeah, that brings us to the third physical root cause of a meltdown. Wire bond and die, attach fatigue. We just discussed the CTE mismatch, warping the heavy base plates, but that same differential expansion is happening on the microscopic scale on top of the chip.
Wow.
You have ultra-thin aluminum or copper wire bonds connecting the top of the silicon die to the circuit board.
And these wires are carrying hundreds of amps.
Yes. And as you push huge amounts of power through this system, over thousands of driving cycles, active power cycling, the silicon die and the copper wire are expanding at different rates. They're literally fighting each other at the weld joint.
So the weld is being sheared back and forth.
Continually.
Yeah.
And eventually, the metal fatigues. The microscopic bonds begin to crack and sever. This is a phenomenon known as wire bond liftoff. Alternatively, the solder material acting as the glue under the chip cracks, causing delamination.
The consequences of that are terrifying because it's a nonlinear compounding failure.
How so?
Well, when those microscopic wires start snapping, you lose electrical pathways. That means the remaining intact wires suddenly have to carry more current, right? Their electrical resistance shoots up, which creates more heat. But simultaneously, because the bond is broken, you've lost thermal pathways, meaning less heat can escape.
It is a textbook death spiral. Electrical resistance goes up, generating more heat. Thermal resistance goes up, trapping that heat. This creates highly localized, deadly hotspots on the silicon. It eventually pushes the silicon past its intrinsic temperature limit, causing complete thermal runaway, melting the die, and triggering an explosive short circuit.
Okay, so everything we just discussed, the TIM pump out, the wire bond shearing, that is what happens over thousands of miles. That is the slow, long-term degradation of the hardware.
Exactly.
But the engineering documentation also details a worst-case scenario that happens almost instantly, a sudden catastrophic spike. They refer to it as transient thermal overload, or the ASC nightmare. What triggers this?
We have to imagine a sudden critical failure in the vehicle's ancillary systems. Say you were driving at high speed, passing someone on the highway. Suddenly, the electric water pump responsible for circulating the coolant fails. Or a piece of debris crushes a cooling line. You instantly lose all convective cooling.
The water just stops moving.
But the heat is still being dumped into it. Or consider a more complex electrical failure, the resolver sensor.
What is that?
This is a highly sensitive magnetic sensor that tracks the exact angular position of the motor's rotor. The motor controller needs to know exactly where the magnets are so it can time the switching of the AC phases perfectly.
Right, if it loses track of the rotor, it's firing blindly.
Exactly. If the controller loses that positional data at high speed, it absolutely cannot safely apply power. If it misfires, the magnetic fields could violently oppose the physical rotation of the motor.
Wait, meaning it could mechanically tear the drivetrain apart or instantly lock the wheels?
Yes.
Oh, that's bad.
So the system recognizes it is flying blind and has to immediately shut down. But it can't just turn off, can it?
Well, this is where we run into the physics of back electromotive force, or back EMF, right? A spinning electric motor is essentially a giant generator. The permanent magnets on the rotor are spinning incredibly fast past the copper coils in the stator. That motion induces a massive voltage in the coils.
If the motor controller just opens all the transistor switches and disconnects the battery to save itself, that high voltage has nowhere to go.
So the voltage would just spike to infinity.
Or, practically speaking, it would spike until it violently punches through the electrical insulation of the wires and the chips, completely destroying the inverter.
Wow.
So the controller cannot just open the switches. The safest thing to do in this terrifying scenario is to intentionally short-circuit the motor. It commands an emergency state called an active short circuit, or ASC.
It deliberately shorts the motor phases together to contain the generative energy.
Yes.
But doing so means all that energy becomes a massive loop of current.
A steady-state symmetrical short-circuit current. And the documentation outlines just how massive this is. Depending on the motor, we are looking at a peak current of up to 300 and 390 amps.
I really want the listener to grasp the scale of 300 and 390 amps.
It's hard to visualize.
It is. Like a typical household circuit breaker, the one that trips if you run a hairdryer and a microwave at the same time is rated for what, 15 or 20 amps?
Yeah, 15 or 20.
A massive, heavy-duty industrial arc welder used to melt thick steel plates might pull 200 or 300 amps. We're talking about 4,390 amps hitting a piece of silicon the size of a postage stamp.
It is an incomprehensible amount of energy. The heat shock hits the internal chips in a matter of milliseconds. It instantly pushes the power chips far outside their safe operating area, their SOA.
If that thermal load is not managed absolutely perfectly by the system's defenses, the silicon will heat up so fast it physically fractures and fails before you can even move your foot off the pedal.
Which is exactly why the safety standards are so draconian. We've established how fast heat can destroy a power module, either slowly through CTE microscopic tearing, or instantly through a 1,390 amp active short circuit.
Right.
Now, we have to transition into the defensive architecture. How does the vehicle's brain detect this microscopic danger before it's too late?
According to the ASIL D standards, the system has a strict fault-tolerant time interval, an FTTI.
Less than 60 milliseconds.
Less than 60 milliseconds from the moment a fault occurs to the moment the system must diagnose it, react, and place the vehicle into a safe state.
Yeah.
That is the hard deadline to pull the car back from a catastrophic meltdown. To do this, engineers have built a deeply integrated software and hardware co-diagnostic architecture.
It's an amazing system.
It is. It is a layered, overlapping defense system. Let's start at the absolute front lines, the physical hardware sensors.
Okay, so the physical temperature sensors are known as NTC thermistors. NTC stands for negative temperature coefficient.
Meaning?
This means as the temperature around the sensor increases, its physical electrical resistance drops.
So the main computer pushes a tiny sensing voltage through the thermistor. As the module gets hotter, the resistance drops, more voltage makes it through, and the computer can read that change.
Exactly. The thermistors are embedded directly onto the DBC board, the direct bonded copper board where the power chips are mounted. The sensor translates the temperature of the board into an analog voltage signal, typically operating between 0.5 and 4.5 volts. It sends that signal to the main microcontroller using a V80Z, a very high-frequency analog-to-digital converter.
And the beauty of that 0.5 to 4.5 volt window is that it acts as its own diagnostic, right?
Right.
If the wire to the sensor snaps in half, the voltage drops to 0. If the wire shorts to the battery line, it spikes to 5 volts. So if the computer sees 0.1 volts or 4.9 volts, it instantly knows the sensor itself is broken and flags an out-of-range error.
The hardware is constantly monitoring its own integrity.
But I have to push back on the physical reality of this setup.
Okay, push away.
If this NTC sensor is physically glued to the copper board, sitting next to the power chip, isn't there an unavoidable delay? Heat doesn't teleport.
No, it doesn't.
If that switch chip suddenly experiences a 3,390 amp short circuit and spikes in temperature, that heat wave has to physically travel through the atomic lattice of the silicon, down through the sintered silver glue, across the copper traces, and then finally into the NTC sensor.
It has to conduct through the physical mass of the materials.
Right. So isn't there a severe thermal lag between the chip actually overheating and the sensor finally feeling it?
That is the ultimate limitation of physical thermistors, and you've hit on the exact reason they aren't enough on their own. Yes, there's a thermal conduction lag.
How long?
The engineering data specifies that depending on the physical distance and the thermal mass of the board, this delay can be anywhere from 50 to 200 milliseconds.
Wait, 200 milliseconds.
Yeah.
The ASIL D deadline for the entire system to react and save the car is 60 milliseconds. If the physical thermometer takes 200 milliseconds to even realize a fire has started, the chip is already a puddle of slag and the deadline is completely blown.
It is an eternity in electrical engineering. If the system relied solely on the physical NTC sensor, the controller would burn to the ground during a rapid transient event.
Wow.
The sensor is great for monitoring the slow, gradual buildup of ambient heat during a long drive up a mountain, but it is totally useless for an instant short circuit.
So how do they beat the physics of thermal conduction?
By relying on two distinct, incredibly fast saviors to bypass the slow NTC sensor. One is baked into the microscopic hardware, and the other operates purely in mathematical software. Let's look at the hardware savior first. We're talking about smart gate drivers.
These are the isolation driver IC's integrated circuits. The sources mention specific models like the NXP GD3100 or the Infineon Ice Driver chips.
Yep.
These are the components that actually deliver the voltage to turn the big power transistors on and off.
But modern gate drivers aren't just dumb relays passing messages. They have their own microscopic autonomous logic circuits. They sit immediately adjacent to the power switches.
Okay.
And because they are so close, they don't wait for a slow temperature wave to propagate through the copper board. They monitor their own internal junction temperatures.
But more importantly, they are watching the electrical behavior of the power switch itself, looking for a desit condition. Desaturation. Let's explain what that looks like electrically.
When a transistor is told to turn fully on, it enters what we call saturation. It allows current to flow freely, and the voltage drop across the transistor itself is very low, maybe a couple of volts.
Right.
But if a catastrophic short circuit happens, the current spikes massively. The transistor physically cannot handle that much current, so it's pulled out of saturation.
It starts acting like a giant resistor.
Exactly. And because it's acting like a resistor with 1,000 amps flowing through it, the voltage across the transistor suddenly spikes drastically.
So the smart gate driver is constantly watching the voltage across the power switch. If it sees that voltage suddenly rocket upward while the switch is supposed to be fully on, it knows immediately. We are in a massive short circuit and we are about to melt.
And when that gate driver detects that desit spike, it does not wait. It doesn't send a message to the main vehicle computer asking for permission to shut down.
The delay would be too long.
Exactly. The communication delay alone would be too long.
Yeah.
The smart gate driver autonomously executes an emergency shutdown of the power switch.
How?
Under 2 microseconds.
2 millionths of a second. That is incomprehensibly fast.
It stops the current before the heat even has a chance to generate. And simultaneously, as it shuts the switch off, it pulls a specific hardware fault pin, the NFLT pin, low.
Oh, nice.
This sends an instantaneous high-priority hardware interrupt to the main microcontroller. It's the driver IC saying, I just shut everything down to save our lives, figure out what went wrong.
Okay, so that microscopic hardware handles the instantaneous violent short circuits. But what about the middle ground?
The gray area.
Yeah, what about a heavy grinding acceleration, maybe towing a trailer up a steep grade? The heat is building up very rapidly. It's building up too fast for the slow 200 millisecond NTC physical sensor to catch it in time, but it's not an instantaneous short circuit, so there is no desit voltage spike to trigger the 2 microsecond hardware shutdown.
Right.
The chip will still melt, just slightly slower. How does the system catch that?
This is where we get into the pure elegance of the system. We enter the domain of the software oracle. Because the physical world is too slow, the main microcontroller runs a real-time mathematical simulation of the physical world in the background.
Okay.
Specifically, it runs a Cower or Foster RC thermal network model.
A thermal network model. I want to unpack this deeply because the math here is fascinating. An RC network in electrical engineering, that stands for resistor capacitor.
Yes.
But how does an electrical concept apply to predicting heat?
It's a brilliant analogy that engineers use to model thermal dynamics. The software builds a complex digital twin of the module's thermal environment. In this model, they use virtual thermal resistors to represent how difficult it is for heat to move through a specific material.
So the thermal resistance of the silicon, the thermal resistance of the silver paste, the thermal resistance of the copper plate?
Right, and they use virtual thermal capacitors to represent the thermal mass or thermal inertia of those materials. Basically, how much heat energy a chunk of copper can absorb before its temperature actually rises.
Because a massive block of copper takes a lot longer to heat up than a microscopic sliver of silicon.
Precisely. So the microcontroller takes the slow baseline temperature reading from the NTC physical sensor.
Oh.
Then it looks at the real-time electrical data. It knows exactly how many amps of phase current are being pushed to the motor at this exact millisecond.
Wow.
It knows the DC bus voltage. It knows the exact switching frequency of the transistors.
Which means, using the I²R conduction loss and the switching loss math we talked about earlier, the computer knows exactly how many watts of heat energy are being injected into the silicon die right now.
Exactly. It feeds that injected heat energy into the mathematical RC thermal network. The math simulates how fast that heat will spread through the virtual resistors and fill up the virtual capacitors.
Which implies that the software can calculate and predict what the internal core temperature of the junction temperature, or TJ, is right now, mathematically, before that physical wave of heat ever reaches the actual physical sensor.
It is a transient junction temperature observer.
Right.
It's literally predicting the present.
That is wild.
If the software map calculates that the silicon core has just hit 160 degrees Celsius based on the current load, the system will instantly trigger a defensive thermal response, even if the slow physical NTC sensor on the board is still only reading 100 degrees.
That is just brilliant engineering. It's like seeing the flash of lightning and knowing the math of the speed of sound. You know exactly when and how loud the thunder will be, so you cover your ears before you even hear it.
Great analogy.
Okay, so the system, whether it's triggered by the 2 microsecond gate driver, the physical NTC sensor, or the mathematical software oracle, detects that it's getting too hot. What is the fallback strategy? What actually happens to the vehicle when the car realizes a meltdown is imminent?
The system's response is beautifully graded based on the severity of the threat. It doesn't just instantly shut off the car on the highway at the first sign of heat, because losing power on the highway is a massive safety risk in itself.
Right, that would be terrible.
There are stages. Let's look at a mild overtemperature event first. Say the calculated junction temperature crosses 125 degrees Celsius and is steadily approaching the 150-degree limit. The system enters a state called thermal derating.
The driver experience of this is exactly like leaving your smartphone sitting out on a table in the blazing hot sun at the beach.
Yes, exactly.
You pick it up and the screen is super dim, the processor is lagging, and apps won't open. The phone hasn't turned off, but it is intentionally choking its own performance to drastically reduce the amount of internal heat it's generating, hoping the ambient air will cool it down.
That's a perfect everyday analogy. In the dual motor controller, the system intervenes in the torque control loops. It smoothly chokes the requested torque output. It might limit the maximum available torque to 30% of its rated capacity.
So if you're the driver, you have your foot pinned to the floorboards trying to accelerate up a hill, but the car just stops giving you power. You might think the engine is broken, but it's actually saving its own life.
And crucially, it doesn't just instantly snap the power from 100% down to 30%. If it did that, the sudden deceleration would violently jerk the car, potentially causing a loss of traction.
Oh, true.
The software derates the torque at a perfectly smooth rate. The documentation specifies a reduction rate of 500 newton meters per second. The goal is to aggressively reduce the joule heating and switching losses so the liquid cooling system can catch up without the driver losing predictable control of the vehicle.
But what if that smooth derating isn't enough? What if the temperature blows right past 150 degrees and crosses into the severe overtemp red zone greater than 175 degrees Celsius?
Yeah, we are in a critical emergency. This is where that 60 millisecond FTTI deadline kicks in.
Okay.
The system must immediately lock out and transition to a definitive safe state to prevent a fire. But how it shuts down depends entirely on the kinetic physics of the car specifically, how fast the vehicle is moving.
Because as we discussed earlier, shutting down an electric motor at 100 kilometers an hour is a radically different physics problem than shutting one down in a parking lot.
Yeah, exactly. Let's look at the high-speed scenario, anything over roughly 80 kilometers per hour. We talked about back EMF. If the system executed an active open circuit, just shutting off all the switches to protect the battery, the fast-spinning rotor would act like a massive generator.
And pop goes the insulation.
The back EMF voltage would spike uncontrollably and blow right through the controller's insulation. So instead, the system is forced to execute a stepwise active short circuit, or a stepwise ASC.
We mentioned the active short circuit before intentionally shorting the motor to contain the voltage, but why stepwise? Why not just instantly short all the phases?
Because if you take a motor spinning at 10,000 RPM and instantly slam all three phases into a short circuit, the resulting transient asymmetrical overcurrent is so violent it could shatter the mechanical gear train.
Yikes.
Or cause a massive instantaneous braking shock that could send the car into a spin. So the software executes a highly choreographed two-step dance.
It eases into the short circuit.
Yes. First, it looks at the exact magnetic angle of the rotor. Based on that angle, it shorts just two of the motor phases together. This suppresses the initial transient electrical shock.
Okay.
It holds that two-phase short for a microscopic window, about 1.5 milliseconds, just long enough for the current to stabilize. Then it drops the final phase into a standard three-phase short circuit.
And the sources note that successfully executing this stepwise short circuit clamps the dangerous DC overvoltage back down to under 720 volts, saving the power chips from an overvoltage explosion.
It contains the voltage, but remember, the energy hasn't disappeared.
Right.
It's now circulating as massive short circuit current. The power chips are going to get incredibly hot handling that recirculating current. So the software utilizes one final trick, an alternating ASC strategy.
How does that work?
The inverter has a top bridge of transistors and a bottom bridge. The software will command the short circuit through the top bridge for a moment. Then, before those top chips can melt, it will switch and route the short circuit through the bottom bridge.
It's passing the burden back and forth.
It's exactly.
It's literally juggling a bomb between two hands so neither hand gets burned.
It spreads the thermal dissipation perfectly evenly, so no single die reaches its melting point before the aerodynamic drag and rolling resistance can bring the car down to a safe speed.
And what happens when it gets down to a low speed under 20 kilometers per hour?
At low speeds, the rotor is spinning slowly enough that the generated back EMF voltage is below the safety threshold of the inverter components. There is no risk of an overvoltage explosion.
Oh, nice.
So the system switches strategies, it executes an active open circuit, it simply cuts all the gate signals, isolating the motor from the battery, it lets the motor freewheel, completely shutting off the current, and the vehicle just safely coasts to a stop.
The software orchestration there is breathtaking. The fact that all of this, the 2-microsecond hardware interrupt, the Foster RC thermal predictions, the stepwise alternating short circuits is happening invisibly while you listen to a podcast on the highway is mind-blowing.
It really is.
But even a 2-microsecond software shutdown isn't foolproof. If the physical board cannot dissipate the heat, if the physics of the module are inherently flawed, the software is just watching it die. How do engineers alter the physical blueprint to prevent this?
This brings us to the design phase. We move from the software layer down to the physical blueprints. In automotive engineering, this is heavily governed by the DFMEA, the Design Failure Mode and Effects Analysis.
Right.
The strict standards demand that you physically design out the flaws before a single line of software code is ever written.
Let's look at the first physical mandate in the design specification, DG PCS TH001. It requires a mandatory 3D dynamic thermal fluid co-design, which means you can't just bolt a flat aluminum heatsink onto the bottom of the power module and run a hose over it.
A flat plate is far too inefficient. When fluid flows over a flat plate, friction causes the fluid closest to the metal to slow down, creating what's called a laminar boundary layer.
Okay.
That slow-moving layer of water acts as an insulator, preventing the fresh, cold water from pulling heat away from the metal.
So how do they break that insulating boundary layer?
The design mandate requires the use of pin-fin, or microchannel heat sinks. Instead of a flat plate, the bottom of the power module is covered in hundreds of tiny, precisely machined metallic pins, or deep microscopic channels.
It vastly increases the physical surface area that is in contact with the coolant.
It does, but more importantly, it creates massive fluid turbulence. The water has to violently crash through this forest of metal pins. That turbulence completely destroys the laminar boundary layer, forcing highly efficient forced convection heat transfer right at the absolute source of the heat.
Right.
The engineering mandate dictates that this specific physical design must force the thermal resistance from the module casing to the heat sink down below 0.1 Kelvin per watt.
Which mathematically guarantees a thermal safety margin of at least 25 Kelvin, even when the module is running at absolute maximum continuous load. So they've optimized the fluid dynamics of the water cooling. But earlier we talked about the internal chips physically cracking and tearing away from the board because of that violent thermal expansion fatigue. How do they design that flaw out of the system? Because I have to ask, why isn't traditional soldering good enough anymore? The entire electronics industry has run on solder for decades.
Solder is phenomenal for your television, your laptop, or your smartphone. But traditional tin-based solder alloys have physical limits.
Okay.
When you subject a layer of tin solder to the extreme, violent thermal cycling of a 390 amp motor controller, the metal rapidly fatigues. The grain structure of the tin deforms under the shear stress of the CTE mismatch. Microcracks form, propagate, and the joint fails completely.
Wow.
The automotive industry recognized that standard solder was a dead end for high-power EVs. They needed a material revolution.
And they found it in nanosilver sintering. AG sintering.
Yes, the DFMEA bill of materials strictly mandates the replacement of conventional solder with nanosilver paste for the die-attached layer, the critical layer, gluing the silicon chip to the substrate.
Using pure silver sounds incredibly expensive for mass-produced cars.
It is significantly more expensive up front, but the performance is so vastly superior that it justifies the cost by eliminating warranty failures and allowing for smaller, cheaper cooling systems. We need to talk about the physics of sintering, because it is not the same as melting solder.
Right, because pure bulk silver melts at 960 degrees Celsius. If you heated an electronic circuit board to 960 degrees to melt silver onto it, you would instantly incinerate the silicon chips and the circuit board. So how do you attach them using silver?
You use nanoparticles of silver. In material science, there's a phenomenon called melting point depression.
Melting point depression.
Yeah. When you take a material and grind it down into microscopic nanoparticles, the surface area to volume ratio becomes so extreme that the surface energy of the atoms is drastically altered.
The atoms on the outside of the particle are desperate to bond with something.
Exactly. So engineers apply a paste made of these silver nanoparticles between the chip and the board. They apply pressure, and they heat it to only about 250 degrees Celsius. Because of that high surface energy, the silver atoms begin to diffuse across the boundaries of the particles, fusing together into a solid, continuous metallic lattice.
Wow.
They bond atomically without ever actually reaching a liquid melting state.
That is just black magic material science. You fuse it at 250 degrees, but once the atoms are locked into a solid bulk structure, the melting point of that join reverts to the bulk property of pure silver, 960 degrees Celsius.
Which means it will absolutely never remelt or weaken under the 150-degree operating temperature of the motor controller. And the thermal properties are staggering. Sintered silver has a thermal conductivity of roughly 200 watts per meter Kelvin. That is 3 to 5 times better at moving heat than traditional tin solder.
It acts like a thermal superhighway, channeling the heat away from the microscopic hotspots on the chip instantly.
And its mechanical yield strength is vastly superior to solder. It almost completely eliminates the thermal fatigue, shearing, and cracking we discussed earlier. It maximizes the power cycling lifespan of the entire module.
Okay, the thermal design is brilliant, but there is an electrical design mandate in the blueprints that caught my eye. The requirement for an active Miller clamp combined with a negative bias design.
Oh, yes. This is crucial.
The documentation outlines a highly specific electrical phenomenon where that extreme DBDT, that violently fast change in voltage when the SiC chip switches, can actually trick the transistor's gate into opening when it's supposed to be firmly closed.
This is a notorious and dangerous issue with high-speed switching, particularly with silicon carbide. It is driven by parasitic capacitance, specifically Miller capacitance. Inside the physical architecture of the transistor, there are microscopic, unintended capacitors formed between the internal layers of the silicon.
Unintended, meaning engineers didn't put a capacitor there. But physics dictates that whenever you have two conductors separated by an insulator, a capacitor exists.
Exactly. So when the voltage on the main power terminal of the switch skyrockets incredibly fast, high DVDT, that rapid change in voltage pushes a tiny spike of current backwards through that internal parasitic capacitor and directly onto the control gate of the transistor.
The control gate is the trigger. If you apply a positive voltage to the gate, the transistor turns on.
And if that backward spike of current raises the voltage on the gate high enough, it accidentally triggers the transistor. It turns itself on without the main computer ever commanding it to.
Wow.
Now remember, we have a top switch and a bottom switch and a bridge. If the bottom switch is legitimately on and the violent voltage swing accidentally triggers the top switch to turn on at the same exact time,
You have a direct, unimpeded short circuit from the positive battery terminal straight to the negative terminal, a shoot-through short circuit. It would instantly vaporize the chips.
it is a catastrophic failure mode. So how do engineers design the circuit board to ensure that gate stays absolutely shut no matter how violent the electrical noise gets?
Well, think about a heavy door that is supposed to be shut. The high DVDT parasitic capacitance is like a massive, violent gust of wind blowing through the hallway. The wind is so strong that it forces the door to blow open on its own.
Good analogy.
If you just let the door rest in the frame, which is like telling the transistor gate to sit at 0 volts to stay off the wind, will easily blow it open.
Just have to actively fight the wind. The blueprints mandate a negative 5-volt bias for the gate turnoff. So instead of just telling the gate to relax at 0 volts to turn off, the driver actively pulls the gate down to negative 5 volts.
You are pushing the door shut with a lot of force. But they don't even stop there. They deploy the active Miller clamp.
The AMC. When the gate driver commands the transistor to turn off, it watches the gate voltage drop. As soon as that voltage drops safely below 2 volts, the active Miller clamp circuit engages.
What does it do?
It acts like an aggressive electronic deadbolt. It forcefully, physically shorts the gate terminal directly to the negative ground potential.
So no matter how hard that DVDT wind blows backward through the chip, the deadbolt holds the gate firmly locked.
Yeah.
The parasitic current is instantly drained to ground, completely eliminating the possibility of an accidental turn-on.
The precision required to maintain that level of electrical safety is immense. And that precision mandate extends to the smallest, seemingly most insignificant components on the board. Look at the analog front end, the AFE-RC filters.
These are the tiny components that process the analog voltage signal coming from the physical NTC temperature sensors before they hit the computer.
Right. And remember, this entire circuit board is operating inside an enclosure that is regularly reaching 150 degrees Celsius. Heat doesn't just melt things, it changes their fundamental electrical properties.
Okay.
A standard cheap resistor might have a resistance of 10,000 ohms at room temperature. But if you heat it to 150 degrees, that resistance might drift up to 11,000 ohms.
Which would totally corrupt the temperature readings. The main computer would calculate the voltage based on the wrong resistance and think the chip is perfectly cool when it's actually melting.
If the resistor drifts, your entire software oracle gets fed garbage data, and the multi-layered safety architecture completely collapses.
So the DFMEA mandates a strict lock-in on the bill of materials. The engineers aren't allowed to just buy whatever cheap resistors are available on the market.
No way.
The RC filters are strictly required to use highly precise thin film resistors. The specs demand a 0.1% accuracy tolerance and a temperature coefficient of less than 25 parts per million per degree Celsius.
Which means mathematically, even if you roast that resistor in a 150-degree oven, its resistance value will barely move a fraction of a percent.
And they pair those ultra-stable resistors with Class 1 CODAG ceramic capacitors. C0G, also known as NP0, stands for negative positive zero. It means the capacitor experiences virtually zero capacitance drift under extreme thermal or voltage stress.
Perfectly stable.
This guarantees that the differential signal symmetry of the temperature data remains absolutely mathematically perfect, even when the environment around it is completely hostile.
That is the essence of a perfect physical blueprint. The design is robust. But here is the hard truth of automotive engineering. A perfect blueprint, utilizing nano-silver, microchannel heat sinks, and C0G capacitors is completely useless if the factory builds it with microscopic manufacturing flaws.
The theoretical design meets the messy reality of the assembly line, which brings us to the manufacturing floor. The PFMEA, the process failure mode, and effects analysis. The controls put in place here border on obsessive, justified paranoia.
Let's go right back to that nano-silver sintering process. We established it is a miracle material that outperforms solder in every way. But it only works if it is applied flawlessly.
Right.
The sintering process requires perfectly distributed pressure and temperature. If the pressure is uneven, or if there's a microscopic speck of contamination, tiny air bubbles voids will be left trapped inside the solid silver layer after it cures.
And as we discussed with the thermal paste, air is a thermal insulator. Those trapped voids act like tiny roadblocks for the heat, creating intense microscopic hotspots on the bottom of the silicon die.
So the factory has to ensure absolutely zero critical voiding. But how do you find a microscopic air bubble permanently trapped between a solid piece of opaque silicon and a solid sheet of copper?
You can't just put an inspector at the end of the line with a magnifying glass. You have to look through the solid metal.
The manufacturing standard, PFMEA, requires 100% inline voiding control. This isn't batch testing where they check one unit out of 100. Every single module produced must pass through an automated scanning acoustic microscope, a SAM, or a 3D automated X-ray inspection machine, an AXI.
Acoustic microscopy. They are literally submerging the module in a fluid coupling medium and firing ultra-high frequency sound waves into the solid metal.
It relies on acoustic impedance. The sound waves travel smoothly through the solid copper, the solid silver, and the solid silicon. But when a sound wave hits a pocket of air, the density changes so drastically that the sound wave violently reflects back to the sensor.
Wow.
The machine maps these echoes to build a perfect, high-resolution 3D map of the internal silver layer, revealing every single microscopic air bubble.
And the automated rules are merciless. The computer calculates the total area of the voids. Total voiding across the entire thermal layer must be less than or equal to 5%. And critically, no single isolated void can be larger than 1% of the total area.
Because one large void concentrated under a critical part of the silicon die will cause a localized hotspot and melt the chip, even if the rest of the layer is perfect.
And what happens if the acoustic microscope scans a unit and finds a single void that is 1.2%?
The machine does not ask a human for an opinion. It does not flag it for manual review. The automated production line instantly locks down, That unit is physically quarantined and scrapped, and the machine halts the line until the process engineers figure out exactly what parameter deviated in the sintering press to cause that void.
That total ban on human variability carries over to how they apply the thermal paste as well. The tin that sits between the module and the liquid cooler, the manual explicitly bans any manual scraping or application.
You absolutely cannot have a factory worker standing on the line applying thermal paste with a squeegee or a syringe. Human hands apply uneven pressure, they leave streaks, they trap air. The factory utilizes full auto, high-precision stencil printing to apply the paste.
And immediately after the robotic printing, the board slides under a 3D laser profiler. The laser scans 100% of the units in real time, mapping the exact microscopic topology of the wet paste.
It is looking for absolute volumetric uniformity. The thickness of the paste must be perfectly calibrated to exactly 50 micrometers, not 40, not 60. 50 micrometers, with an allowable tolerance of just plus or minus 10 micrometers.
The width of a human hair is roughly 70 micrometers, so they are printing a layer of paste thinner than a human hair, and the laser confirms there are absolutely zero microbubbles, streaks, or imperfections on the surface, ensuring the absolute minimum contact thermal resistance before it gets bolted down.
Let's move on to the electrical connections. We talked about those ultra-thin aluminum and copper wire bonds on top of the chip tearing off due to thermal fatigue. How does the factory ensure those initial welds are absolutely perfect before the module leaves the plant?
They use automated ultrasonic wire bonding machines. These are fascinating because they don't use heat to melt the wire like a soldering iron.
No, they use friction. The machine presses the ultra-thin wire against the silicon pad and vibrates it at incredibly high ultrasonic frequencies.
It's like rapidly rubbing two sticks together to start a fire, but at an atomic level with metal. The violent ultrasonic friction scrubs away the microscopic oxide layers on the surface of both metals, exposing pure atoms. The pressure then forces those pure atomic lattices to share electrons and permanently fuse into a solid metallurgical bond.
It's a perfect atomic weld, achieved in milliseconds. But the factory doesn't just assume the machine did it right. The bonding machine dynamically tracks the ultrasonic energy delivered, the microscopic physical deformation of the wire, and the exact downward pressure applied for every single individual wire on the board in real time.
That's a lot of data.
It plots this data into a closed-loop feedback curve. If a single weld on the board deviates from the perfect mathematical curve by a fraction of a percent, the entire module is rejected.
And even with that real-time digital monitoring, the quality control engineers still don't trust it, because the sources say the factory requires mandatory destructive testing every single shift.
They absolutely do. Real-time data is great, but physics is truth. Every single shift, the engineers pull sample modules directly off the production line and literally tear them to pieces.
They perform a pull test where a microscopic hook grabs the wire and pulls straight up until the wire physically snaps. And they perform a shear test where a tiny chisel pushes against the side of the weld joint until it fractures.
They measured the exact number of grams of force it took to destroy the weld. They are proving, physically, that the metallurgical bond is robust enough to survive the brutal thermal cycling it will face in the real world.
We built this flawlessly using ultrasound. Now let's violently rip it to shreds just to prove we aren't lying. I love the rigor of that. Now, there is one final factory test outlined in the PFMEA that really stands out. We know the module has liquid cooling channels.
Right.
Obviously, you cannot have pressurized water leaking out onto a circuit board carrying 800 volts and 390 amps. But when they test the integrity of the heatsink assembly on the line, they don't test it for leaks using water. They don't even use compressed air. They use helium leak testing. Why helium?
It all comes down to atomic physics and molecular size. Water molecules, H2O, are relatively massive and complex. Nitrogen and oxygen molecules, which make up the air we breathe, are also quite large. But helium is a noble gas. The helium atom is incredibly tiny. It has an atomic radius of about 31 picometers.
It is practically the smallest, sneakiest atom in the universe.
So after the heatsink is fully assembled, the factory pressurizes the internal cooling channels with pure helium gas to 4 bar, which is roughly 58 psi. Then they place the entire assembly into a vacuum chamber and use a highly sensitive dual-stage mass spectrometer to sniff the vacuum for any stray helium atoms.
So the logic is foolproof. If a microscopic fracture or a porous seal is so infinitesimally small that a highly pressurized tiny helium atom cannot even squeeze its way through, then big, fat, complex water molecules have absolutely zero mathematical chance of ever leaking out during the lifespan of the cause.
Exactly. It completely guarantees the integrity of the high-voltage isolation barrier. It totally eliminates the terrifying risk of a water leak, bridging the gap between the phases and causing a deadly high-voltage short circuit.
Okay, so let's summarize where we are. We have a module that was mathematically modeled to perfection. The design utilizes microchannel cooling and nano-silver sintering. On the factory floor, acoustic microscopes confirm the silver is void-free. Lasers map the thermal paste to within 10 micrometers. The ultrasonic wire bonds were destructively tested. And a mass spectrometer proved the water jacket can hold pressurized helium. If a module survives this gauntlet, it's finally ready to be put into a consumer's car, right?
Not even close.
Really? What else is left?
We enter the final, most brutal stage of automotive engineering. The DVP&R, the Design Verification Plan and Report. This is where engineers take a batch of these perfectly designed, flawlessly manufactured modules, bring them into a laboratory, and try as hard as they possibly can to completely destroy them.
The ultimate torture test. They have to prove that the flawless module will remain flawless after 10 years of real-world abuse. Let's look at the first torture chamber, the power cycling endurance test, which is governed by the IEC 6074934 standard. What are they doing to the module here?
This test aims to find the true structural fatigue limit of the module's materials. They place the controller on a test bench and forcefully push massive, continuous pulses of load current through the silicon chips. The goal is to rapidly heat the chips up, intentionally forcing a massive temperature fluctuation, a delta T.
A thermal swing.
Yes, and they mandate a delta T of at least 80 Kelvin, often pushing it to a 100 Kelvin swing. So they violently heat the chips up, turn the power off, and blast it with cold water to crash the temperature, and then immediately heat it up again, over and over.
And how many times do they subject the module to this violent thermal shock?
The standard requires 100,000 to 200,000 continuous cycles.
200,000 times. What does that replicate for the end consumer?
It simulates over a decade of aggressive, harsh, worst-case scenario driving. It replicates the driver stomping on the accelerator to pass a truck, braking heavily, and driving up a steep mountain grade in the dead of winter, day after day, year after year. It tests the absolute thermal mechanical limits of the nano-silver sintering and those ultrasonic wire bonds we talked about. They are trying to force the metals to shear and fatigue.
And the acceptance criteria at the end of the test are incredibly strict. After surviving 200,000 extreme thermal shocks, the engineers measure the thermal resistance of the module. It is not allowed to have degraded by more than 10% from its brand new baseline. The electrical voltage drift across the power chips must be less than or equal to 5%.
And then they take the module, which has just been abused for weeks, and put it back under the scanning acoustic microscope.
And the scan must show absolutely zero delamination in the silver layer and zero wire bond liftoff. After 200,000 cycles, the internal metallic structure has to essentially look brand new.
It mathematically proves the absolute limit of the module's lifespan safety. But the power cycling test only focuses on thermal and electrical stress. In the real world, cars bounce over massive potholes, they drive on corrugated gravel roads, they hit speed bumps. Physical kinetic vibration is a massive enemy of electronics. That brings us to the ISO 16753, or the LV124 standard.
The shake and bake test. The technical terminology is high vibration and rapid thermal cycling composite stress testing. They take the power module and bolt it to a massive mechanical shaker table, and they violently vibrate it on 3 different spatial axes. The frequencies they sweep through range from 10 hertz all the way up to a screaming 2,000 hertz.
They are hunting for the physical resonance frequencies of the circuit board. Every physical object has a frequency where it vibrates sympathetically, magnifying the kinetic energy. If they find that frequency, the board will literally try to shake itself to pieces. And the acceleration forces are immense, a random acceleration root mean square of 35 meters per second squared.
It is violently shaking the module. But that's just the shake part. While this table is violently vibrating, the entire rig is enclosed inside an environmental chamber.
And the chamber is rapidly flash freezing the module down to minus 40 degrees Celsius, letting it soak in the freezing cold, and then instantly flooding the chamber with heat to boil the module at positive 150 degrees Celsius.
And the engineers run this composite torture test continuously for over 500 hours while pushing massive operational power through the unit.
That is over 20 straight days of non-stop violent 3-axis shaking, combined with freezing and boiling thermal shock under electrical load.
And after 500 hours of this, the criteria for passing are unforgiving. The DBC copper board and the microchannel heatsink must show absolutely zero macroscopic or microscopic mechanical cracking. The thermal paste cannot have dried out or washed away. The tiny NTC temperature sensors we discussed earlier must still read perfectly accurate to within 1 degree Celsius.
But the most critical test after the shake and bake is the dielectric integrity test.
Right, because if the violent shaking rubbed a wire bare, or if the thermal shock cracked an internal insulator, high voltage could jump to the chassis of the car.
Exactly. So the engineers hit the battered circuit board with 500 volts DC. They measure the resistance between the high voltage lines and the ground. It must maintain an insulation resistance of over 100 megaohms with absolutely no electrical arcing, tracking, or dielectric breakdown. The electrical fences must remain perfectly intact.
It is honestly a miracle of human engineering that anything built by us can survive that kind of punishment. But there's one final boss in the DVP&R sequence. Up to this point, they have proven that the physical hardware won't break. The metal holds, the welds hold, the paste holds. But they still have to prove that the software oracle and the complex algorithmic safety fallbacks actually work in the real world when a catastrophic failure does happen. This is the HIL fault injection test.
ADL stands for hardware in the loop. This is the most dynamic and terrifying test. They take the full motor controller and physically mount it to a massive laboratory dynamometer. It is connected to a physical electric motor. They spin that motor up to a screaming 12,000 RPM under maximum high-speed, high-torque load.
The system is operating at the absolute razor edge of its maximum performance. The chips are dumping heat, the coolant is rushing through the microchannels, and then the engineers intentionally sabotage the system in real time.
They inject fatal faults. They will flip a switch and instantly simulate a total coolant pump failure, bringing the forced convective cooling flow to absolute zero in a fraction of a second. Or they will electronically manipulate the NTC temperature sensor signal, forcing it to instantly jump from a safe 80 degrees to a critical 150 degrees Celsius, feeding the computer a phantom thermal shock.
And this is the moment of truth for that 60 millisecond FTTI deadline we talked about in the very beginning. The instant the engineers trigger the sabotage, the clock starts. The system must mathematically prove that it recognized the catastrophic error, diagnosed it correctly, and completely transitioned the spinning motor into a definitive safe state in 60 milliseconds or less.
And remember, because the motor is screaming at 12,000 RPM, the system cannot just open the switches. It is forced to execute that complex stepwise active short circuit sequence we discussed. The laboratory instruments measure everything in real time. They measure the transient DC bus overvoltage during the exact microsecond the short circuit engages, ensuring the software successfully clamped the back EMF voltage under 720 volts so the chips didn't explode.
They measure the maximum asymmetrical short circuit current, proving the alternating phase strategy kept the current under 550 amps so the silicon didn't vaporize.
But the ultimate metric, the one that directly affects the human being sitting behind the steering wheel, is the torque degradation rate.
The torque drop. If a motor suddenly executes an active short circuit at 12,000 RPM, it could act exactly like ripping the emergency brake handle up on the highway.
The HIL dynamometer meticulously measures the physical torque output on the drive shaft during the 60 millisecond shutdown. The torque drop must be perfectly algorithmically smooth. The requirement states that the driver cannot feel a sudden, jarring braking shock greater than 50 newton meters. The transition must be seamless, ensuring that even during the most catastrophic hardware failure imaginable, the driver maintains safe, predictable, and calm mechanical control of the vehicle.
Which brings us full circle. Let's take a breath and zoom out to recap this incredible journey. We started this deep dive looking at the microscopic physics of thermal accumulation inside a tiny silicon die, the friction of flicking a transistor on and off thousands of times a second. We looked at how that immense heat warps base plates, pumps out thermal paste, and literally tears atomic wire bonds apart.
We explored the brilliantly elegant defensive systems. The 2 microsecond hardware interrupts fighting sudden shorts, and the predicted Foster RC thermal software models calculating the future of heat before the physical sensors even know the chip is hot.
We saw the engineering marvel of the physical blueprints breaking fluid boundary layers with microchannel heat sinks and using the surface energy of nanosilver to create atomic welds at low temperatures. We looked at the paranoid perfection of the factory floor using lasers, acoustic microscopes, and atomic helium mass spectrometers to guarantee absolute perfection. And finally, the brutal 500-hour shake-and-bake vibration chambers and 12,000 RPM dynamometer sabotage testing.
It is a staggering, overwhelming depth of engineering rigor. And it is all entirely driven by the uncompromising mandate of ASIL D safety standards. Every single conceivable physical failure mode is anticipated, mathematically modeled, physically engineered out of the blueprint, and then violently tested to destruction to verify the fix.
all designed to keep you safe on the road, completely invisibly, while you just enjoy the quiet hum of the air conditioner. But I want to leave you, our listener, with a forward-looking thought based on the sheer scale of the engineering we just unpacked. We have built an incredible multi-layered defense hardware, software, materials, testing for the electric dual motor systems of today.
But the EV industry is not slowing down. The demands for performance are only increasing. We are pushing toward even higher switching frequencies to increase efficiency. We are demanding unimaginable RPM limits from the motors, and we want to pack all of this power into incredibly dense, lightweight form factors. The motors are getting smaller, yet pushing vastly more power.
Which means the heat density is only going to skyrocket. Will this current paradigm of silicon and silicon carbide, cooled by water and glued together with silver, eventually hit a hard, unbreakable physical limit?
That is the big question, keeping material scientists awake at night. Eventually, even the magic of nanosilver and the predictive brilliance of thermal software algorithms might not be enough to cheat the fundamental laws of thermodynamics.
Exactly. What radically different materials or entirely new cooling methodologies will we have to invent next just to keep up? Will we have to move away from ceramic substrates and start building power chips directly onto synthetic diamond wafers to channel the heat? Will we have to completely submerge the bare silicon directly into boiling dielectric fluids to pull the heat away fast enough? Because the invisible war of physics raging under the floorboards never stops. It is only going to get hotter. Keep questioning how the machines around you actually work. Keep learning, and we will see you next time on The Deep Dive.